In this lecture, I am going to present Introduction to Moment Distribution Method, procedures, absolute and relative stiffness of the members, carryover factors, distribution factor, sign convention for moments, and application of moment distribution method to continuous beam and rigid frames. First, coming to the introduction, as we know, analysis of indeterminate beams and frames by the method of slope deflection involves solving a number of simultaneous equations, which is tedious and time consuming. The moment distribution method is a displacement method of analysis. Essentially, it is a method to solve the simultaneous equations in the slope deflection method by successive approximations by hand that may be carried out to any desired degree of accuracy. Basically, moment distribution method is an iteration procedure. This method was suggested by Professor Hardy-Cross in early 1930s at the University of Illinois. It is considered one of the most important contributions ever made to the structural analysis of the continuous beams and rigid frames. Therefore, this method is called a Hardy-Cross method. This method begins with the assumption that all the joints in an indeterminate structures are fixed temporarily against rotation and displacement. The fixed end moment induced by the loading on the spans are written down at each joint. Then the joint is released one at a time in succession. Because of the release of joints, unbalanced moment arise at the joints. These unbalanced moments are distributed at the joints in a proportion to their distribution factor of the members meeting at the joints. Then the half of the distributed moments are carried over to the far end of the members. Because of the carryover moments at joints, again unbalanced moments are created which are further distributed and carried over. In this manner, the iteration is performed in a successive cycles of operation till the values at the joints become insignificant. At this stage, the iteration is stopped and the moments at each joint is algebraically summed up. The sum of the moments at the end of each span at a joint is the required final end moment. So this is analyzing statically indeterminate beams and frames by simple hand calculation, and this can be generally suitable for high degree of indeterminate structures. Then coming to the procedures, in this method artificially restraining temporarily all the joints against rotation and writing down the fixed end moments for all the members. The joints are then released one by one in succession. At each release joints, the unbalanced moments are distributed to all the ends of the members meeting at that joint. A certain fraction of these distributed moments are carried over to the far end of the members. Then the release joint is again restrained temporarily before proceeding to the next joint. The same set of operations are carried out at each joint till all the joints are completed. This complete one cycle of operations. The process is iterated for a number of cycles till the values obtained are within the desired accuracy. Then coming to what is absolute and relative stiffness of the members. The absolute stiffness of a member can be defined as the moment required to produce a unit rotation at the simply supported end. It is also known as member or absolute stiffness factor. Look at this figure. Here A is the simply supported end and B is the fully restrained end. So this is the moment MAB, anti-clockwise moment MAB, and this is the theta A is equal to the rotation at the end A is equal to 1, and here at the support B due to fixed end, here the slope is 0, and this is the moment MBA. MAB, absolute stiffness of a member AB, when theta is equal to 1. MAB is equal to 4EI by L, this is equation 1, and the moment at the further fixed end is MBA. MBA is equal to 2EI by L, so this is equation 2. The ratio I by L in equation 1 and 2 is known as the relative stiffness and is denoted by K. It is also known as member relative stiffness factor. For prismatic member AB, the relative stiffness KB is equal to KBA is equal to IAB divided by LAB. Then what is joint stiffness factor? When many members meet at a point, it is called a joint. Each member meeting at the joint has its own stiffness factor. Then each member its own stiffness contributes its share in resisting the total rotation of the joint. According to the principle of superposition, the total stiffness factor of the joint is the sum of the member stiffness factor of all the members meeting at that joint. That is Kj, the total stiffness factor at joint, is equal to the summation of K. That is the stiffness factor for all the members which are meeting at the joint. Then coming to what is carryover factor. If a moment MAB is applied at the end A of member in figure 1, a specified amount of moment MBA is generated at the further restrained end. The carryover factor is defined as the factor by which the moment at simply supported end A, MAB, is multiplied to get the moment carried over to the other end, that is MBA. That is MBA is equal to CAB into MAB. So this is equation 3, where CAB is the carryover factor. From equation 1 and 2, from these two equations, from equation 1, MAB is equal to 4EI by L, and from equation 2, MBA is equal to 2EI by L. So CAB is equal to MBA divided by MAB. As you know, MBA is equal to 2EI by L and MAB is equal to 4EI by L. So this ratio is equal to half. The carryover factor is equal to half. Thus, for a prismatic member, carryover factor is always half. If the further end is hinged end instead of a fixed end, as in figure 2. This is the figure 2. So here the further end B is the hinged end instead of the fixed end. So here this is the moment MAB at end A, and the moment at the end B, MBA is equal to 0. This is theta is equal to 1. So the corresponding stiffness is known as the modified stiffness of a member. So MAB is equal to 3I by L, and the relative stiffness K dash is equal to 3 by 4 into K. And the moment carried to the further hinged end, that is MBA, is equal to 0. Then coming to what is distribution factor. Consider a joint in a structure where 2 or more members meet. If an external moment M is applied to such a joint, the joint undergoes a rotation theta as shown in figure 3. So look at this figure. So here, due to the moment applied at the joint, so the same rotation takes place in all the members which are meeting at the joint 1. So this is 1 3 member, this is 1 4 member, this is 1 5 member, this is 1 2 member. So 4 members meeting at joint 1. So at joint 1 the moment applied, that is M. So due to this moment all the members rotate the same amount, that is theta. Since all the members meeting at this joint undergo the same rotation theta, the applied moment M is distributed to each of the ends of the members according to their relative stiffness values. The factor by which the applied moment is multiplied to obtain the end moment of any member is known as the distribution factor. This is denoted by dF, distribution factor. Consider the free body diagram of joint 1 in figure 4. So look at this figure. This is the free body diagram of joint 1. So this is joint 1, and here the 4 members meeting 1 2, 1 3, 1 4 and 1 5. So this is the moment, applied moment, and here at the end of the member 1 2. So this is the moment M12, and this is the moment at the end of the member 1 3, M13, and at the end of the member 1 4, this is the moment, and at the end of the member 1 5, this is the moment M15. For equilibrium of joint 1, we have M12 plus M13 plus M14 plus M15 minus M is equal to 0. This is equation 7. So here take the equilibrium of the joint 1. So this is the moment anti-clockwise direction, and here these are the moments clockwise direction. M12 clockwise direction, M15 clockwise direction, M14 clockwise direction, and M13 clockwise direction. So take the sum of the moment at the joint 1 is equal to 0. That is M12 plus M13 plus M14 plus M15 minus M is equal to 0. The end moments of member can be written in terms of the angle of rotation theta. So as you know, in slope deflection method, M12 that is equal to 4e k12 theta, and M13 that is equal to 4e k13 theta, and M14 is equal to 4e k14 theta. M14 is equal to 4e k14 theta, and M15 is equal to 4e k15 theta. So these are the moments at the end of all the individual members. Substituting these values in equation 7. So substituting these moments in equation 7, so that is M is equal to M12 plus M13 plus M14 plus M15. So here put the value M12, that is 4e k12 theta, M13 4e k13 theta, M14 4e k14 theta, and M15 4e k15 theta. So after substituting these values, so M is equal to 4e k12 theta plus 4e k13 theta plus 4e k14 theta plus 4e k15 theta. Then M is equal to 4e theta bracket k12 plus k13 plus k14 plus k15. So this is the summation of the relative stiffness of the member. So M is equal to 4e theta into summation of k. Then theta is equal to M by 4e summation of k. So this is equation 10. Summation of k is the sum of the relative stiffness of all the members meeting at the joint 1. Then substituting the value of theta in equation 8. So this is the value of theta from equation 10 and substitute in equation 8. So this is the equation 8. M12 is equal to 4e k12 theta, M13 is equal to 4e k13 theta, M14 is equal to 4e k14 theta, M15 is equal to 4e k15 theta. So here you put the value of theta. So after putting the value of theta here, so M12 is equal to 4e k12 into M by 4e summation of k. So here 4e cancel each other. Then M12 is equal to k12 divided by summation of k into M. So this is equation 11. The ratio k12 by summation of k indicates the fraction by which the applied moment M is to be multiplied to get the moment registered by member 1, 2. So, this ratio is called the distribution factor. The distribution factor for any member AB defined as RAB is equal to KB divided by summation of K. That is, the distribution factor for the member AB is equal to the relative stiffness of the member AB divided by the sum of the relative stiffness at joint A. Then coming to the sign convention for moment. So, as you know, in slope deflection method, here also you have to take the same sign convention. All clockwise moments are positive and all anti-clockwise moments are negative. So, this is the positive moment clockwise and this is the negative moment anti-clockwise are the joints. Then the application of moment distribution method. The rigid joint structures can be analyzed by moment distribution method, and this method can be applied to the following structures. So, first to the continuous beam and to the rigid frames. So, the continuous beam can be solved without sinking of support and with sinking of support. Similarly, the rigid frames can be solved frames without side sway and frame with side sway. So, these are the different cases. Easily you can analyze the beams and rigid frames by using the moment distribution method. Then coming to the analysis of continuous beam and frames by moment distribution method. So, what are the different steps used for the analysis of continuous beam and frames by moment distribution method? So, first assume all ends of a beam are fixed and find the fixed end moments. Then the second step, that is calculate the relative stiffness of the members, then calculate the relative stiffness of the joints, then calculate the distribution factor for all the members meeting at a joint. Then balance a joint by distributing balancing moment to various members meeting at the joint proportional to their distribution factors. Do similar exercise for all the joints. Then carry over half the distributed moment to the far ends of the members. This upset the balance of the joint. Then repeat steps 4 and 5 till distributed moments are negligible. Then sum up all the moments at a particular end of the member to get the final moment. So, these are the steps you have to remember during the analysis of continuous beam and frames by moment distribution method. Then how you have to find out the fixed end moments for different loading conditions. So, look at this figure. Here the load is present at the midpoint of the fixed beam. So, due to this load, so the moment fixed end moment at the end A, MFAB is equal to minus WL by 8 and MFBA is equal to plus WL by 8. And look at this figure. Here the load is eccentrically present, that is at a distance A from the support A and B from the support B, and the length of the beam is L. So, here the fixed end moment MFAB is equal to minus WAB square by L square, and this side the moment MFBA is equal to plus WA square B by L square. And look at this figure. Here the uniform distributed load is present throughout the span and the length of the beam is L, and here the fixed end moment MFAB is equal to minus WL square by 12 and MFBA is equal to plus WL square by 12. And here the load is present, that is at a support A W and at the support B 0, and the triangular loading, the varying loading is present on the beam AB and the length of the beam is L. So, here the fixed end moment at the end A, that is MFAB is equal to minus WL square by 20 and MFBA is equal to plus WL square by 30. Then look at this figure. This is also varying load and the maximum intensity, that is at the midpoint W, and at both ends the intensity is 0, and the total length of the beam is L, and here the piston moment at the end MFAB is equal to minus 5 by 96 WL square, and MFBA is equal to plus 5 by 96 WL square. Similarly, here the moment which is applied at a distance small a from the support A, anti-clockwise moment, and due to this moment the piston moment induced at the end of the member MFAB is equal to minus M by L square B into B minus 2A, and MFBA is equal to minus M by L square A into 2B minus A. So these are the piston moments you have to remember when you will find out the piston moments. Then coming to how the relative stiffness of the member, relative stiffness of the joint, and the distribution factors are calculated. So first coming when ends A and D are fixed. So look at this figure. So this is the continuous beam. Here the support A fixed and support D fixed, and these are the intermediate support. So due to the fixed support at A and D, the slope theta A and theta D is equal to 0, and at the intermediate support the slope, that is theta B and theta C. Length of the span AB is L1 and moment of inertia I1, and length of the span BC L2, moment of inertia I2, and length of the span CD L3 and moment of inertia I3. So first you find out what is the relative stiffness of the member KB, KBA, KBC, KCB, and KCD is equal to KDC. So KB is equal to KBA is equal to I by L1, and KBC is equal to KCB is equal to I2 by L2, and KCD is equal to KDC is equal to I3 by L3. This is relative stiffness of the members. Then find out the relative stiffness of the joints. So here this is one joint, this is another joint. So at joint B, so how many members meet? That is KBA and KBC. And at joint C, how many members meet? KCB and KCD. So KB is equal to KBA plus KBC, and KC is equal to KCB plus KCD. So you know the relative stiffness of the members. So here you put the relative stiffness of the members. KB is equal to KBA plus KBC, I1 by L1 plus I2 by L2. Similarly, KC is equal to KCB plus KCD, that is equal to I2 by L2 plus I3 by L3. So these are the relative stiffness of the joints. Then after knowing the relative stiffness of the joint, then you can find out the distribution factor for the members. So as you know, due to fixed end at A, the distribution factor is 0. Similarly, fixed end at D, the distribution factor RDC is equal to 0. And for all other members RBA, RBC, RCB and RCD, that you can find out. So RBA is equal to KBA divided by KB. So KBA you know I1 by L1, KBA I1 by L1, and KB you know I1 by L1 plus I2 by L2. This is. Similarly, RBC is equal to KBC divided by KB. So you know KBC is equal to I2 by L2, and KB is equal to I1 by L1 plus I2 by L2. I1 by L1 plus I2 by L2. Similarly, RCB is equal to KCB divided by KC is equal to I2 by L2 divided by I2 by L2 plus I3 by L3. Then RCD is equal to KCD divided by KC is equal to I3 by L3 divided by I2 by L2 plus I3 by L3. So these are the distribution factors that you can find out after knowing the relative stiffness of the members and the relative stiffness of the joints. Then the second case, that is when ends are simply supported. Here look at this figure. Here the end A simply supported and end D simply supported, and BC are the intermediate support. So here due to simply supported at end A and D, so this is the rotation theta A and theta D takes place, and at the intermediate support the rotation is theta B and theta C. And the span AB length L1 and moment of inertia I1, span BC length L2, moment of inertia I2, span CD length L3 and moment of inertia I3. So here you can find out the relative stiffness of the member AB, BC and CD, but as the end is simply supported, so you can find out modified relative stiffness of the member for the span AB and for the span CD. At the end A and D are simply supported. So for the end span KB, KBA, this is equal to 3 by 4 I1 by L1. Similarly for span CD, KCD is equal to KDC is equal to 3 by 4 I3 by L3. And for the intermediate span, you can find out the relative stiffness KCB is equal to KBC is equal to I2 by L2. For intermediate span, you can take the relative stiffness I by L, and for the end span, if the end is simply supported, so you can find out the relative stiffness, that is 3 by 4 I by L. So this is the relative stiffness of the members. KB is equal to KBA is equal to 3 by 4 I1 by L1. KBC is equal to KCB is equal to I2 by L2. KCD is equal to KDC is equal to 3 by 4 I3 by L3. Then you can find out the relative stiffness of the joint at joint B. So you can find out the relative stiffness, that is by taking KBA plus KBC. And at joint C, you can find out the relative stiffness KC is equal to KCB plus KCD. So here KB is equal to KBA plus KBC 3 by 4 I1 by L1 plus I2 by L2, and KC is equal to KCB plus KCD is equal to I2 by L2 plus 3 by 4 I3 by L3. Then after knowing the relative stiffness of the joint and the relative stiffness of the members, then you can find out the distribution factor of the members. So as the end is simply supported, so the distribution factor at the end is 1. RAB is equal to 1. Similarly, RDC is equal to 1 due to simply supported end. And for all other ends of the members, you can find out the distribution factor. So for RBA, you can find out KBA divided by KB, and RBC you can find out KBC divided by KB, and RCB is equal to KCB divided by KC, and RCD is equal to KCD divided by KC. So these are the distribution factor. RBA is equal to KBA divided by KB is equal to 3 by 4 I1 by L1 divided by 3 by 4 I1 by L1 plus I2 by L2. Similarly, RBC is equal to KBC by KB is equal to I2 by L2 divided by 3 by 4 I1 by L1 plus I2 by L2. And RCB is equal to KCB by KC is equal to I2 by L2 divided by I2 by L2 plus 3 by 4 I3 by L3. And RCD is equal to KCD by KC is equal to 3 by 4 I3 by L3 divided by I2 by L2 plus 3 by 4 I3 by L3. So these are the distribution factors that you can find out. Coming to when end A is fixed and end is simply supported. Here one side is fixed and other side is simply supported, and these are the intermediate support BC. And here at the fixed end, the slope theta is equal to 0, and at the simply supported end, the slope, that is theta d, and at the intermediate support, the slope is theta b and theta c. And this is the moment of inertia and length of span AB, and this is moment of inertia and length of span BC, moment of inertia and length of span CD. So here you can find out the relative stiffness of the span AB by taking moment of inertia by length of the span, and for intermediate span BC, the relative stiffness is equal to KBC is equal to KCB is equal to I2 by L2, and at the end span CD, so as the support D is simply supported, so here you can find out the relative stiffness of this member is equal to 3 by 4 I3 by L3. So this is the relative stiffness of the members. KB is equal to KBA is equal to I1 by L1, KBC is equal to KCB is equal to I2 by L2, KCD is equal to KDC is equal to 3 by 4 I3 by L3. Then you can find out what is the relative stiffness of the joints. So KB is equal to KBA plus KBC, and KC is equal to KCB plus KCD. So here KB is equal to I1 by L1 plus I2 by L2, and Kc is equal to I2 by L2 plus 3 by 4 I3 by L3. So these are the relative stiffness of the members and joints. Then you can find out the distribution factor of the members. So at the end A is fixed, the distribution factor for that end is 0, and at the end D is simply supported, the distribution factor at this end is equal to 1, RDC is equal to 1 and RAB is equal to 0, and for all other ends of the members the distribution factor can be determined. RBA is equal to KBA by KB is equal to I1 by L1 divided by I1 by L1 plus I2 by L2. RBC is equal to KBC by KB is equal to I2 by L2 divided by I1 by L1 plus I2 by L2, and RCB is equal to KCB by KC is equal to I2 by L2 divided by I2 by L2 plus 3 by 4 I3 by L3, and RCD is equal to KCD divided by KC is equal to 3 by 4 I3 by L3 divided by I2 by L2 plus 3 by 4 I3 by L3. So these are the distribution factors that you can find out when one end of the continuous beam is fixed and other end is simply supported. So this way you can find out the relative stiffness of the members, relative stiffness of the joints, and distribution factor for the members. So after knowing the distribution factor and fixed end moments, then you have to go for the distribution of the moments, then carry over the moment to the far end of the members. In this manner the iteration is performed in successive cycles of operations till the values at the joints become insignificant. Then the iteration is stopped and the moments at each joint is algebraically summed up. Then the sum of the moments at the end of each span at a joint is the required final end moment. Then after knowing the final end moments, then you can draw the bending moment diagram as you drawn in slope deflection method. So in similar way you can draw the bending moment diagram. So first you have to draw the support bending moment diagram, then you have to draw the positive bending moment diagram due to the presence of the external loading. After cancel of positive and negative, the net diagram is the final bending moment diagram. Then by taking separately each span, you can find out the reactions at the end of each span. Then you have to find out the shear force at different positions. Then you can draw the shear force diagram. This is the procedure. You have to analyze the continuous beam or the rigid frames by moment distribution method. Now all are clear.